Hello, hi guys. So my name is Shaurya, and today I'm going to be presenting my project to you, which is denoising gravitational wave signals using deep learning. So the main idea behind this project is that LIGO detects space-time ripples that are gravitational waves that are some of the most profound discoveries in modern physics. So these are small distortions in the fabric of space-time itself. Gravitational waves are basically ripples in spacetime caused by massive accelerating bodies, for example, merging black holes or neutron stars. These are incredibly faint and these are covered in noise while detecting. So, by using deep learning architecture, I am aiming to suppress the noise and get the signal. Okay, so first let's learn a little bit about gravitational waves. Uh, the first time these were discovered was 2015, which is recent, so there haven't been like a huge number of breakthroughs in trying to get the signal. The signals are incredibly faint and covered in a lot of noise. So each waveform encodes critical astrophysical information. For example, the masses of the objects, their spin orientation, their orbital dynamics. And this is key to understanding how our universe works and key to discovering and understanding faraway objects. The problem with this kind of detector noise is that it has non-Gaussian characteristics. Real detector noise, it exhibits complex properties that are significantly different from Gaussian distributions. It shows non-stationary behavior. The noise spectrum can vary over time due to multiple different kind of factors. Even quantum vacuum effects and the smallest seismic tremors can add a lot of noise. The deep learning advantage is that a complex neural network can detect all these kind of different noises and can filter these out dynamically and can give you the real signal, which is very faint and maybe with a lot of accuracy. So conventional filtering techniques, which are highly effective under idealized conditions, they usually use Gaussian noise. However, this real data produces a real challenge as well. So the hypothesis is that deep neural networks can directly learn the intricate patterns and distinguish a signal from the noise. Detector noise. So this is a sample of detector noise. This is only 5 seconds long, and this is from a period where it is known that no gravitational event was occurring. And so this means that this is just the static background noise that detectors see all the time. Okay, so the problem statement is that we're building an intelligent denoising system. The goal is to build a deep learning model that can accept noisy strange signals directly from LIGO detector and it outputs clean and physically accurate gravitational waveforms, the underlying signal that is behind all that noise. And this approach treats denoising as a supervised learning problem, and the network learns from noisy observations and it outputs real signals. So we give raw LIGO strain data into the model, and the model is basically a deep convolutional architecture which is trained to separate the signal from the noise. The denoised output still preserves the physical characteristics and can be used to study various objects like black holes or neutron stars. The key technical challenges with this kind of approach is that the realistic noise is a bit complex. It is very different from normal Gaussian distributions, which can easily be modeled. Slightest changes can lead to huge amounts of noise. So the model must be able to generalize across this variability. There is a huge amount of signal diversity as well. Gravitational wave signals can vary dramatically in amplitude and duration, and it completely depends on the source parameter, the masses of the two objects, their spins, and their orientations. Even physical validity is different. So the goal of this extends beyond simple signal smoothing. The reconstructed waveform that we get must be physically realistic in order for it to be useful. It should preserve the frequency evolution of the gravitational signal, their phase relationships, and amplitude characteristics that encode critical astrophysical information. So these constraints, it requires a careful design and consideration, and we should be able to balance noise suppression with a good amount of signal detail. So first step is data preparation. We have to acquire real LIGO noise. We can do that using the gravitational wave Open Science Center's detector data. And specifically, I downloaded about 1000 seconds of data from the LIGO Hanford Observatory during the O2 observing run. The real noise captures all of the complexities of actual detector operation: seismic coupling, thermal noise, quantum shot noise. You can see how little the magnitudes of these noise are, but the actual gravitational signals are also very weak. It is like of the order of 10 to power minus 18 or something. And you can see how these different noises they contribute to the total detector noise. Even stuff like quantum vacuum can contribute to the noise. So the processing pipeline that we had was we downloaded this data from the GWOSC archive. We segmented it into 1 second windows, and then I applied quality checks to make sure the glitchy parts of it are excluded. And then I stored it in the HDF5 file format for rapid access. So then I generated clean training signals. So the real clean training signals cannot be fully obtained because there is no method yet to completely get clean gravitational wave signals. So the best way to do this is to generate and model these signals on our own. So I created a data set of about 5,000 clean target signals, which is coupled with the noise signals in order to create the actual data set on which the model is trained. I randomize the parameters, taking different masses for objects, taking different spins and different positions from the source, and then I normalized all the values to the 1 second duration that is consistent with the detector sampling rate, making sure that the inputs are uniform and the dimensions are the same. So this parameter diversity ensures that the model encounters a huge diverse amount of data and it can correctly predict actual detectors. This is one of the examples of the clean target signals that I produced. So from this, we add both of the noise and the signal. So this is the signal which is overlaid on top of the noise, and you get the final output. And you give this as the input to the model while training, and this is the expected output that the model should have. And then we train it according to that. We have a parameter alpha which controls the signal to noise ratio. And then I randomly assign this between 5 to 20 dBs to make sure that I have a variety of data. And then applied band pass filtering to focus on sensitive frequency band. Of course, then I whitened the noise and the signal using the detector. And then I created paired data sets, which I then fed into the model. This generation pipeline closely reproduces real LIGO observations, and the network can learn real denoising strategies which can be applied on actual detections. Okay, so the model that I used was a convolutional autoencoder. The reason for which was that it can capture local structure quite well and can represent data into a lower dimensional space, which focuses the network to learn on the actual data and it kind of discards noise. It also preserves detail. It directly links encoder layers to decoder layers, enabling the network to preserve high frequency details which it normally might not be able to. The network architecture design was inspired by a unit, which is basically a series of convolutional blocks which have an increasing channel depth, followed by max pooling for downsampling. It captures hierarchical features from local oscillations to global structure. It reduces the bottleneck of the noise by using autoencoders. And then, of course, there is a decoder stage which transposes convolutions to upsample the representation back to original dimensions. which reconstructs the clean waveform. The skipping connections part makes direct pathways from encoder to decoder, preserving fine-grained details, which is otherwise not possible. Another thing that we use is residual learning. So the model, instead of predicting the clean signal immediately, what it does is it predicts the noise in the signal that we gave it, and then it subtracts the noise from the total signal, which finally gives us the clean signal. And the clean signal is checked to see if it matches the actual clean signal based on which the model is trained. The benefits of doing this is there is an enhanced training stability. It makes sure that details are preserved quite well, and it makes sure that the signal is detailed and the final output has minimal loss. The ability to isolate and remove noise, it translates into a higher detail of the final output, and it makes sure that the scientific data that is stored in the gravitational wave signal is still available for numerical analysis. So there is an optimizer called Adam used in this model, which is used because of its adaptive learning rate, and it efficiently handles sparse and scarce gradients and noisy problems, making it well suited to be used for this particular application. The loss function that we are using is a hybrid loss function which combines the mean absolute error and a and a correlation penalty. This makes sure that the network learns to accurately predict both the amplitude of the signal and its characteristic waveform shape, which is critical for preserving the integrity of a gravitational wave signature. I first used a different loss function, which was just using the mean absolute error, but that was not giving good results. And using this hybrid loss function gave much better results than the previous. The training process was just data iteration multiple times, train the model over the data multiple times, and use a function and the Adam optimizer, which corrects the parameters of the model and makes sure that the model actually fits the data. It is trained over multiple epochs. I trained it over 100 epoch with a batch size of 32, and through back propagation, the gradients are computed, and the Adam optimizer it updates the network's parameters, like I said. And then there is a dedicated validation set, which is different from the training set. And we see the model's performance on unseen data, and we ensure that it actually fits to unseen data and it is not just overfitted on the training data. The training setup. So I utilized over 5,000 prepared samples that I prepared with an 80-20 ratio. So basically 80% of the samples were used for training and 20% for validation. There was a batch size of 32 that was used, which was a balance between different gradient estimates and efficient memory utilization during the training process. I trained it on my local computer only using my GPU, and it took, I think, about 10 to 15 minutes to train the model. The model had about 30,000 parameters that needed to be adjusted. So the learning rate was initially 10 to the power minus 4, which is a common choice for deep learning models. And to enhance robustness, we employed early stopping to prevent overfitting. The entire training process, like I said, was performed on my NVIDIA RTX 3050 GPU, and the model consistently converged without showing signs of overfitting. This is what the training curve looked like over different epochs. This is the training loss and the validation loss, and it goes down over every epoch. The quantitative results are shown here. The mean squared error was 0.147. The mean absolute error was 0.303. The R square value was 0.28. The SNR gain was 2.9 dBs, and the noise reduction I got was around 50%. This is a plot of the output. This is the input signal that was fed into the model, and this is what its predicted output was, and this is the actual output. You can see the error as well. There is another example here, and there are multiple examples for this. Okay, so The key takeaways from this is that the model successfully demonstrates that deep learning can effectively reconstruct gravitational signals from noisy detector data, which is a robust alternative to conventional filtering techniques. It showed enhanced feature extraction. The residual unit architecture was able to learn multi-scale features. The high fidelity and physical realism of the model should match what was actually expected from it. And this establishes a promising pathway for integrating this into real-time LIGO data pipelines, which is a huge step forward for astrophysics. Okay, so that was my presentation. Thank you.